In this presentation, we explore building a digital signal processor as a softcore on an FPGA, and we also look at its performance. Here's an outline of the talk. Some key aspects of the talk. The main contribution will be adding explicit DSP operations to an FPGA-based softcore processor. And as you can see at the end of this slide, this results in significant improvements in performance at a modest increase in extra hardware. By way of introduction, a key aspect of digital signal processing is the importance of the convolution operation. So this is an inner loop that multiplies elements of two vectors together and accumulates a sum. And by speeding up this one operation, we can improve the performance of many digital signal processing applications. Traditional digital signal processors from manufacturers such as Texas Instruments and Freescale are different to general purpose processors because they have specialized units for assisting with DSP operations, particularly things like efficient addressing modes and specialist instruction sets. If we look at general purpose processors, the way that they speed up operation is by issuing multiple instructions at once, and often all of these instructions are different. By contrast, digital signal processing operations tend to be much more regular. So we use a SIMD or vector processing approach to speed up those operations. A key component of this research is looking at the internals of one of these operations, so doing the convolution operation. The strategy for this research is experimental and analytical. What we'll do is look at some particular algorithms. We'll build a processor, implement those algorithms on the processor, and compare the performance of various different algorithms and various different processor architectures. All of these operations are designed to speed up a convolution operation, and our goal is to be able to do one multiply accumulate operation every second and to have all the other overhead sitting in the background. So, firstly, in terms of our analytical approach, what we've done first is to take a very simple processor and look at what is involved in the core of the convolution operation. And this works out to be 9 instructions. We need to fetch 2 operands, multiply those together, accumulate the results into a long register, and then we need to increment the index registers for the operands and also test a loop and return to start again. A common enhancement in many processors, DSP processors, but also general purpose processors, is to have a single multiply accumulate instruction. This can reduce the number of instructions in our loop down to 7. So this is the first enhancement. This is called the Mach enhanced processor. The second way that we can improve performance is by having more complex addressing modes. In this case, when we fetch our operands from an index register, we can also automatically increment that index register by the appropriate stride size for the vectors that we're looking at. This reduces the number of instructions down to 5. The last thing that we can do to improve performance is to try and do all of these operations in parallel. That is to be fetching operands, multiplying and accumulating them, and also doing the loop tests all within a single instruction, or at least doing all those instructions in parallel. And so this gives us the final enhancement. This requires some additional hardware support because we need to be able to address both of the operands at once. So we need 2 memories and we need 2 address generators for those memories. We also need to be able to do 0 overhead loop support. So this means before starting the loop, we set up the number of iterations, and that loop counter is tested in parallel with the arithmetic operations. So now, provided we do all of these initialization operations that you can see at the top of the code, then our loop reduces to a single instruction here, a single auto-incrementing multiply accumulate instruction. So we've gone from 9 instructions to 1 instruction, and we would expect a significant improvement in performance. The second part was, after doing the theoretical analysis, to actually build a CPU and test that this actually works in practice. Here in this diagram you can see a simple CPU with a program memory and a single data memory. And we can enhance that through various additional hardware units to improve the performance, as we did in that theoretical exploration. So here's a more complex CPU. The first thing we can do is replace the multiplier by a MAC, so that gives us the first enhancement. Secondly, we can do auto-incrementing registers, which requires a special address generator. And if we add a second memory, we can fetch both operands in parallel. And so this gives us the completely enhanced or dual memory enhanced DSP processor. When we ran this processor, we found the following results. Here are some numerical results that you can look at in the printed paper. I might go to some graphs which will better illustrate the results. This page here shows how much it costs to add the extra features. This table here shows us how much performance increase we get, but as I say, it's easier to look at that in some graphs. So this shows the additional hardware. FPGAs consist of several different components, but if we look just at slices, which are the major component, we can see as we go from base level to adding MAC support, auto-indexing registers, and then dual memories, we slightly increase the amount of hardware required. We also compared our results to a custom general purpose processor called Microblaze, and so our processor is of a similar size to Microblaze. In terms of performance, we looked at performance for 3 algorithms, for an FIR filter and for matrix multiplication. Both of those are based on convolution, and we would expect a significant improvement for those. Fast Fourier transform is quite an irregular algorithm, and so it can't take advantage of the additional DSP enhancements we've put in there. So if we look first at FIR filter and matrix multiplication, so the green and the red bars here, the left-hand axis here is the number of iterations per second for our test programs. And so we can see that we go from less than 50 to more than 250 as we go through our various enhancements for our processor, and that's more than we get from a traditional Microblaze. However, you'll see that for the irregular algorithms, for this yellow one here, there's only a very slight improvement in performance, and the Microblaze gives us significantly better performance. The main reason for the additional performance of Microblaze is that it uses a 5-stage instruction pipeline, and our architecture currently is not pipelined. So if we were to pipeline our algorithm, we would expect another factor of 2, 3, or 4 improvement in performance for DSP algorithms. So just to summarize, the contributions of our work was to develop a softcore DSP processor, to build that processor and to look at the performance and the area of that for various different algorithms. Particularly, we found that our DSP processor can give better results than a RISC processor, and we would expect that to increase if we were able to add pipelining further. So, you saw in the results that the enhancements can improve the area time performance for a very simple processor up to 9 times. And that comes at a fairly small cost, 41% extra cost. More work would be needed to make this a commercial possibility. We would want to pipeline the architecture. We'd then want to look at doing more complex operations, vectors, pipeline processing, etc. So, thank you for your time.